Okay, this is question number 22. A disk rotates steadily inside a disc-shaped container filled with oil of viscosity mu. Assume linear velocity profile with no slip and neglect stress on the outer edges of the disk. Find a formula for the torque M required to drive the disk. Okay, so in this question, they give us this uh, application. However, this is actually to calculate another type to calculate the viscosity. Okay, however, here we are using the torque. We are using the torque as our measurement guide. Okay, previously we are using velocity, means we need to check the velocity of that cylindrical cylinder falling down. So we get the velocity, means we could determine the dynamic viscosity. So in this calculation, because if we have one application like this, so we need to rotate the this here. So when we rotate here, so means we need power. So that power is calculated as torque. So means that if we could determine the torque, we could determine the value of dynamic viscosity. Okay, so and then first we need to understand about the velocity profile, about how these things work. So the idea is we have this structure, and then we put, because here clearance mean we could put fluid inside this area, inside this clearance. Okay. So we put fluid inside this one. Okay, please bear in mind that we cannot use this parameter, this apparatus to measure gas viscosity. Okay, so and then if the fluid here, if the oil, for example, is very thick, the viscosity is very high, so you need more power to rotate at certain desired speed. So means that by knowing the torque, so we could calculate the viscosity of that liquid. Okay, so and then for this situation, we found that the surface that's very critical, that you need to know is the surface at the top here. So and then the surface at the bottom, because this surface is actually the moving surface. So normally, previously we have a two plate like this. So we could draw the velocity profile because the plate is moving at certain velocity and this moving is fixed. Okay. So and then we could draw the velocity profile like this. So for this one is actually we could draw the velocity profile. Okay, but you need to understand that the velocity profile need to draw according to the application. Some student, they will draw the velocity profile like this one. So it's look correct, but I need to make sure that you really understand when you draw like this one. So because this object is rotate at certain speed, so means that, so you need to imagine in a 3D dimension. For example, if you have a disc here, so and then it's rotate at the center point here. So the velocity profile is actually, if we take here, so the velocity profile will become like this. So this is the fixed plate here. So and at the bottom, the velocity profile will become like this one. Okay. So this is in 3D. So I hope you could understand this one, because the molecule here is keep moving at the circular direction, a circular trail like this one. Okay. So if a flat plate like this, okay, moving at certain velocity like this one, so now you can imagine that the velocity is actually, the velocity profile is like this, because it's moving from one point to the point like this one. Okay, so I hope you can understand this, because this is very important, the way you could draw the velocity profile is actually will lead you to the estimation or the simplification of your calculation later on. So and then here in the question they ask to neglect the shear stress on the outer edges, because at this age actually the fluid is still stick on the surface and give resistance. So normally, because the thickness of the disc is very small, commonly around 1 millimeter, so we could neglect, because 1 millimeter we need to use 0.001 meter in our calculation, so maybe it is not give us a big impact in our calculation. Okay, so because we are dealing with a moving part, okay, so we use the idea of torque. So we know torque is Fr, and F here is equal to tau times A, and tau is equal to mu du dy. So we assume there is no slip condition there. So and then here, because we are dealing with a circular like that one, so means that we need to start to calculate in small portion here. Why? Because if we have two points, for example, point number 1 and point number 2 here, we found that the radius is different. Now, you can understand that the radius is different, so means that the torque here is not a constant value. So it's depend on the radius. So when the situation is not constant, so we need to calculate from a small part of them. And then we do the integration, we get the whole value. Okay, so we start with the dq. Dq means a small amount of torque for one small area on that disc, on the disc. So we write dq is equal df times r. So df here is equal to tau dA. So this is tau dA. So and then, okay, so and then the A here is actually the area. So the area here is actually 2 pi r dr. Okay, so how to relate the 2 pi r dr with the area? So it's very simple. So you have A is the area of the circle. So it is equal to pi r square. Okay, so and then if you do the dA dr, so you will have it is to equal 2 pi r. So and then if you want to substitute the value of dA only, so you will have dA is equal to pi r and dr. That's why we use this idea of 2 pi r dr. Okay, so and then, okay, so then we substitute a little bit about the du here. Okay, so u is the linear velocity. So linear velocity means the unit is meter per second, but in rotating this, okay, they are rotate in RPM, okay, or they are rotate using rotational speed. So means that the linear velocity need to be converted into rotational speed. So the equation, the relation is u is equal r omega. So we substitute the u here with the r omega, which is the r here is the radius, and the omega here is the radian per second. Okay. Now, if we substitute everything, you will get these equations. You have mu r omega. So dy here is the gap. So means that we have a rotating cylinder here. So this is the gap. So this is the gap. So we assume that the gap is equal to h. So we substitute with h. So we substitute everything. So we could simplify it as mu omega 2 pi over h r squared dr. And then now we need to integrate each side. We need to integrate both sides. So we integrate the value of dq. So we could get the value of q. And the integration of this one, because it is only integrate with dr. So all this parameter is constant, nothing to do with R. And then we could have R4 over R. So here the limit is actually 0 to capital R, because capital R is the maximum radius in the disc. So and then if you do that, okay, we could simplify that. Because we have a two torque, we have two surface, so means the torque is need 2 times with 2, so it is equal to 2 times mu omega to pi over h r squared over 4, and then we could simplify of this one. So if you see this, so this is a torque, so it is equal to mu omega pi r 4 over h. So means that if we could measure torque that occur on that machine, we could estimate the value of mu, because the radian per second means the rotational speed, the pi, the radius, and the h here is all, it can be measured directly from the machine. So means that this is the way how we could find the value of mu from the top of that machine. So all of this is actually, the rotating disc is called a viscometer. So it means a machine to measure a viscosity. But for the falling cylinder, it is about, we call it as the capillary viscometer. You could search in the internet about the capillary viscometer. So they are using the idea of falling down object. Sometimes they will use sphere, sometimes they will use the cylinder like that. So, and then for the rotating viscometer like this, so you will go for the rotating viscometer. So you will get a viscometer that using this to measure a viscosity.